Hi everyone, we are EC504 Group 6. Our final project is the file reconciler. Our project goal is to design and implement an efficient protocol for reconciling two similar files. We have two minimum requirements. The reconciler must have the ability to reconcile any two ASCII files up to 100 megabytes in size that differ in 5-character edits using less than 50 megabytes of communication and in reasonable time. The reconciler must also have a command line interface and display the amount of time and data transmission used by the protocol. The features in our project are the ability to reconcile arbitrary binary files, the ability to reconcile directories of files, and an Android client. Throughout this presentation, we will be using two terms to distinguish the computers using our reconciler. We define the receiver as the destination system. We define the sender as the source system that has the source files being synchronized.
Our file reconciliation algorithm is largely based on Tregel's Rsync. This algorithm was developed in the 90s out of frustration to solve the problem of synchronizing large code bases over the high latency, low bandwidth dial-up networks of the time. In this presentation, we will explain the three main phases to our reconciliation approach. In phase 1, we must summarize the contents of the receiver's file. First, we must compute an optimal block size as a function of the file size and the expected number of edits. This ensures that our algorithm scales with the size of the input by providing a fine enough granularity to maximize the number of matched blocks without the computational overhead of blocks being too small. We then split the file into blocks of size L. For each of these blocks, we compute a pair of hashes that will be used to quickly find and verify matching blocks. The first hash is the Adler32 checksum. It has two important properties for our algorithm. It is computationally cheap to recompute the checksum on byte offsets of a sliding window. Further, it takes into account both the contents of the block and the order of the bytes stored. The strong hash used is the MD5 hash that we don't expect to collide with another block of data. These hashes are then stored in a hash map. Because the weak hash is not cryptographically strong, we expect it to collide many times. To ensure that we maintain a reference to all blocks, we then chain strong hashes on each collision. Here we have an illustration of phase 1. Starting with file alpha, split the file into blocks of size L. For each block, we compute the pair of hashes and store them into a standard Java hash map. By the end of phase 1, a hash map containing all block hashes and a block size are ready to be sent. In phase 2, we must match blocks on the sender's files to hashes from the receiver. To do this, we make use of the rolling version of the Adler32 checksum for every byte offset of a sliding window in the file. To recalculate the checksum on a single byte offset, all that's needed is the byte leaving the window and the byte entering the window. The computation is then just a constant time sequence of additions. The goal is to find windows that match to a block. On each computation of the weak hash, we query the hash map for a match. This search is also completed in constant time due to the hash map data structure. When there is a match, we verify by calculating the strong hash and comparing it to the found hash. When the verify succeeds, we emit the corresponding block number. Otherwise, if no match can be found, emit a byte of literal data to be sent. Here on the sender side, we have a similar file alpha known as beta. Beta shares many blocks in common with alpha, but due to insertions, deletions, and modifications, some data needs to be transmitted. We define the sliding window pi that creeps along the file beta. On each offset, we compute the weak hash of pi and query the hash map for an array list of strong hashes. If we obtain a list of strong hashes, we then compute the strong hash of pi and search for it in that list. If that succeeds, we emit a step containing the block index. Otherwise, if a block is not matched, then we append a byte leaving the sliding window to the array of the literal data. In the end, a list of steps is generated that will reconcile the file. In phase 3, we perform the file reconciliation. The first step is to load the local file into RAM and split it into blocks that we can reference by index. Using the instructions received from phase 2, we either write out literal data from the instruction or fetch a block from the reference file to write. Once we've completed all the instructions, the aggregate MD5 hash is computed and compared to the hash received at the beginning of the process. In this graphic, we parse the instructions from top to bottom, building the file alpha prime left to right. Alpha is used as a reference for matched blocks to be fetched from.
Our file reconciler uses a TCP socket to communicate between computers. We chose TCP over UDP for several reasons. TCP guarantees that the data transfer remains intact and arrives in the same order in which it was sent. TCP automatically breaks up your data into packets for you. TCP does not have a size limitation per transmission. Lastly, TCP is easy to use. You read and write data as if it was a file. To begin the reconciliation process, Computer 1 executes the reconciler. If there are no computers listening on the reconcile port, Computer 1 becomes the receiver. Afterward, Computer 2 executes the reconciler. Computer 2 sees that Computer 1 is listening on the reconcile port. Computer 2 becomes the sender. All data transmitted between Computer 1 and 2 are serialized objects. To keep track of data used, every transmission between computers contains an integer that indicates the length of the transmission. The reconcile process aggregates the amount of bytes sent and received. To keep track of the time that has transpired during the reconciliation process, a timer is used.
One of the features we selected was the reconcile directory of files. The user can select a path, and all files will be reconciled. The sender's list of files and each of its hash values are sent to the receiving end. Each file and folder on the master list is then searched on the receiving end. If there is a file name match, then the hashes are compared to see if the file contents match. If the file hash does not match, then the index to the sender list is added to a diff list. Folders are not included in the diff list because the program does not recurse into subdirectories.
We also made an Android app. We required that it would be able to reconcile files between both Android and a PC. For this, we used a similar interface as our PC application, which is an input for a file or directory path, input for an IP address. For our Android application, there were several things that were already available to us. That left us with the job of making a file browser with several threads to allow networking to happen. Android doesn't allow you to do networking on the main UI thread. A simple interface, which we could do using the views, and validation, which is simple code to make sure all the inputs are correct. For our file browser, we used a list view activity with an appropriate adapter, which allows us to select any file or directory on the SD card. Using async task, we were allowed to have threading. We used a relative layout, text views, buttons to make the interface. And finally, we wrote validation functions to make sure the IP is correct and to make sure that the file or directory that is chosen exists and is writable. There are a few limitations to our app. For one, on Android, there's a maximum heap size that's determined by the device being used. For our test device, the maximum heap size was 64 megabytes. Larger devices, such as certain tablets, have much bigger max heap sizes. Also, the directory reconciler will not recurse into subdirectories and only reconciles files in a single directory. A few things we could improve upon would be, for one, buffering. This would mean splitting up the file into chunks and not loading the entire thing into RAM at once. If we were to use compression, we could lower the bandwidth at the sacrifice of a little bit more processing power. For multiple files, we could split the program into multiple threads. And finally, for the searching algorithm, we could have put the file list into an AVL tree structure or some sort of tree structure that gives us log n time, instead of our current method, which uses a sorted array list, which works in n squared.